Okay, it's been a bit. I don't think I've seen you guys for a week. Let's get right to it. Exam next week. This is the last of your 3 midterms. 3 midterms. So the exam is next Wednesday. Same procedure as always. You can start early at 7:30. The topics are Chapter 9, which is stress and strain, Chapter 10, gravitation, and Chapter 12, oscillations, which I will finish today. Review session, there is one. It's this Friday, 1 p.m. to 3 p.m., ball 328. I will update Blackboard with the review session information. The formula sheet for the exam will become available sometime today and on Blackboard. And study up. It's hopefully going to be a little better than the second exam, well, a little easier. Not significantly though, so study hard. And hopefully by the end of today's lecture, we'll get to do a few problems of the type that should be on the exam for oscillations. Okay, so oscillations. This is kind of where we were. So we were discussing a mass attached to a spring as an example of simple harmonic motion, right? The idea with simple harmonic motion is it's subjected to a force which is of the form of Hooke's law. So there has to be a restoring force on this system, right? And a restoring force is a force that tries to take the system back to its original configuration, right? So for a mass in a spring, it is the force that the spring exerts when it's stretched or compressed, right? And that is trying to drive the system back to equilibrium. And this thing, because it's moving and there's no force on it at equilibrium, will always overshoot equilibrium, right? So it will go to the other end and come back, right? And this process keeps going on, right? So for this oscillation, right, this back and forth motion, we can discuss a few parameters. The amplitude of the oscillation is always the maximum displacement from equilibrium. Right? The period of the oscillation, the time period, is the time taken for one complete cycle. Right? So it's one complete back and forth motion. And frequency is the number of cycles per second, so it's just the inverse of the time period. Right? So time period and frequency give you the same information. If you know one, you know the other. Right? It's just a measure of either how long a cycle takes, which is the period, or the number of cycles in 1 second, which is the frequency. Period, of course, is measured in seconds, and frequency is measured in hertz. Okay, so that's your general case, right? So you have a mass on a spring subjected to a restoring force of the form minus kx. Right? A simple pendulum, by the way, can be considered an example of simple harmonic motion. We're going to kind of prove that it's simple harmonic motion under a certain condition, right? But the basic idea of a simple pendulum is it's a mass attached to a light string and it just oscillates back and forth, right? Like that. A grandfather clock, which I've never quite figured out why it's called a grandfather clock, but that's what it is. A grandfather clock has a pendulum, right? A pendulum is keeping time. Because the idea is every single oscillation takes a fixed amount of time. So you count how many oscillations and you know how much time has elapsed. Everyone following me so far? Okay. So now let's see if a simple pendulum is simple harmonic motion. Right? Our condition for simple harmonic motion is that the restoring force is minus kx, some constant times the displacement. Right? If I can show that this system is experiencing a force like that, which is causing it to oscillate, right, then this motion is simple harmonic. So tell me, which force is responsible for making this thing oscillate back and forth? There's no spring here. Which force causes a pendulum to oscillate? You can yell out the answer at me. Gravity, right? Okay. There's gravity acting on this system, and that's what's causing it to go back and forth. But gravity acts straight down, right? So if I were to draw the free body diagram of a simple pendulum, it looks like that, right? It's actually not that complicated. There's just a lot of stuff in that drawing. let's say this is the undisplaced position. This is the pendulum, right? It has some mass. And for this case, we're assuming that all the mass of the pendulum is in that bob that's hanging on the end, right? The pendulum itself, the string, is very light compared to that, so we're ignoring the mass of the string. Okay, so the force on this, of course, is mg, straight down, correct? Right? This is displaced by some angle theta, and we know this is going to do this, right? It's going to oscillate like this, correct? That means I need a force, like when I pull this way, I need a force going this way, right? To take it back to its original position. Does everyone see that? Right? I need a force pointing back to the original position, right? That's what a restoring force is. Right? It's trying to take the bob back to where it originally was. Everyone with me? Okay. There are two forces acting on this bob, of course. What is the second force? Apart from its weight, what else acts on it? Tension. Right? There's tension in the string. And that's acting along the string that way. Right? So I have two forces, this guy and this guy, neither of which seem to be taking me back to where I started. Right? The solution, of course, is that one component of mg is actually going this way. Right? This is essentially the same thing as a block on an incline. Right? Just like with a block on an incline, there is that component, mg sine theta, pushing it down the incline, right? There is actually the same component, mg sine theta, pulling it back towards where it was, right? So you guys do not need to know the derivation, but it's good to know why this is true. So this angle is theta, this angle is theta, right? Because these two lines are parallel and this line intersects them. If this angle is theta, this component of mg is mg cosine theta. It's adjacent. And this guy is mg sine theta. Right? So what we're saying here is that mg sine theta is the force responsible for trying to take this thing back to its original position. So like you said, it is gravity, right? It's one component of gravity, the component acting to take it back to original position, right? The tangential component in this case. Everyone see that? Okay, now if you remember Hooke's law, right, said the force that's trying to take it back must be of the form minus kx. Right? So a force that's like Hooke's law is some constant times the displacement. Right? So we have to show that this force, mg sine theta, satisfies Hooke's law. Right? That it is some constant times the displacement. Okay? And the displacement in this case is this arc. Right? For the bob, the displacement is however much I've moved it. Everyone follow that? Right? So what we're saying is the force on this needs to be proportional to that displacement. Right? And the force we have, of course, is mg sine theta. The sine is accounted for because, yes, it is opposite to x. If x goes this way, mg sine theta is pointing this way. If x goes that way, mg sine theta is pointing this way. Right? So mg sine theta is in the direction of a restoring force. It's trying to take it back to its original position. Right? So the minus sign is okay, but I don't have an x. Right? I want a constant times an x. And that comes from here. Right? For small angles, right, when theta is small, sine theta is approximately equal to theta. Right? That is an approximation. And when that approximation is true, this force becomes minus mg theta. Right? And if we measure theta in radians, we can relate it to the length of arc. Remember this from rotation? Right? Or has everyone blanked rotation from their minds already? So, theta in radians is the length of this arc divided by the radius of this circle, which is the length of the string. Right? The radius of the circle that the bob swings in, right, this guy, is the length of the string. Right? So, if x is displacement, theta in radians is x over L. Right? That was the whole point of using radians to begin with, right? I could talk about displacements and arc lengths and radii. Which means my restoring force is minus mgl divided by L times x. Looks like this, right? M is a constant, G is a constant, capital L, the length of the string, is a constant, right? So what this is telling you is that the force on the simple pendulum, right, is a restoring force. It's a constant times the displacement, right? And the value of that constant in this case is mg over L. Everyone following me? Right? So what we know is that this thing is going to oscillate back and forth with the time period given by 2 pi under root m over k. Right? The same as a mass on a spring. Everyone following me so far? Right? Now let's do m over k for this. K for this case, right? If I compare this to f equals minus kx, right? This is the same equation as this if k is equal to mg over L. Everyone follow that? Right? F equals minus kx is the same as f equals minus mg over L times x if k is mg over L. Right? So now, the time period of this oscillation, which is defined as 2 pi under root m over k, becomes 2 pi m divided by mg over L, which is 2 pi under root L over g. So that is the time period of a simple pendulum. Right? The frequency, if I know that's the time period, frequency is defined as 1 over t. So it is 1 over 2 pi under root g over L. Right? You don't need to memorize the formulae. I'll give you the formulae. Right? But you need to understand what they stand for. Right? So what we're saying here is a simple pendulum is simple harmonic motion under one assumption. What was my assumption? What makes this true? Small theta, small angles. Right? So under a small angle assumption, this is simple harmonic motion. Right? And notice one thing about the time period of a simple pendulum. What does it not depend on? Doesn't depend on mass. Right? Unless unlike the mass spring system, right, where the time period did depend on mass. Right? The time period of a simple pendulum does not depend on mass. Right? So think of two little kids on a swing. Right? So everyone's been on a swing at some point in their lives, right? And you can imagine two little kids on a swing. One is slightly heavier than the other. Right? Does it matter to their time periods? It doesn't. Is everyone following? That's what we mean when we say it's independent of mass. Right? The time period for a simple pendulum depends purely on the length of the pendulum and the acceleration due to gravity that it experiences. Okay, so let's get back to the presentation. And this is all that this is saying. This curve over here, right, this guy, is showing you where that sine theta equals theta approximation is true. Right? The blue curve is the sine theta curve. The red curve is theta. Right? So the region where they're the same, right, is when theta is small. As theta gets larger, they're not the same anymore. Right? And then this motion isn't simple harmonic. Everyone with me? Right? The reason we were able to say it's simple harmonic is because we were able to say that the restoring force on it is a minus kx. Right? As soon as that approximation fails, right, the restoring force on it is not minus kx anymore. Right? There is a restoring force on it, but it's not of the form of minus kx, so it's not simple harmonic motion. It will oscillate, but it's not SHM. Right? What that means is it doesn't have this time period and it doesn't have this frequency, and it will probably depend on the amplitude of the oscillation. Okay? But for us, we stick with SHM, so if you see a pendulum, assume small angles. Okay, unless of course it explicitly says large angles. Okay, so this is what we found. we can write the time period and the frequency in this form for a simple pendulum. Right, let's see if you guys are awake. Four different pendulums, four different frequencies. I'm asking you to tell me which one of them is the longest. So what that means, of course, is analyze how F depends on L. The equation is right there. So I'm looking for large L. Am I looking for a small f or a large f? No, I'm not clicking to see where everyone's at just yet. I want you guys to actually think this through. Okay. We're at two extremes now. You've given me either the highest frequency or the lowest frequency is what it looked like. So if you look at that equation, right, are F and L directly related or indirectly proportional? Indirectly, right? L is in the denominator on the other side. So if I increase L, what happens to F? It goes down, right? So the largest L corresponds to the smallest F. Everyone see that? Okay, so click the appropriate response. As this guy gets bigger, this guy gets smaller. So the largest value of this guy corresponds to the smallest value of this guy, which is this. Right? So, yep. Right, this is the one with the heavy kid and the light kid. Very good. The period is the same. If I ask the same question for a mass on a spring, right, the period is dependent on the mass. Right? For a mass on a spring, T is 2 pi under root m over k. Right? The larger the mass, the more the time period. For a simple pendulum, since the restoring force is also proportional to mass, right, it was mg over L, right? So there was an m dependence on the restoring force. Right? That's why the m goes away. It cancels out. Right? So for a simple pendulum, it doesn't matter, but for an ordinary mass in a spring, the mass does matter. Okay, so click something. So in order to answer this, think of the time period of a simple pendulum. Its T is 2 pi under root L over G. So the period of a pendulum is directly proportional to L, right? The length of the pendulum. Correct? So if I increase the length of the pendulum, which by the way means moving the bob downwards, right? That's increasing the swinging length of the pendulum. Right? If I increase the swinging length of the pendulum, I increase the time period. So what you need to do is figure out whether you need to increase the time period in this case or decrease the time period in this case. If it's running too slow, does that mean its time period for an oscillation is too long or too short? What does a clock running slow mean? Too long a time period or too short a time period? Too long, right? So if the time period is too long, What do I need to do to L to fix it? Sure. This making sense? So the adjustment would be move the weight up, right? That would shorten the swinging length of the string. Yep. Oops. New question. The time period of a simple pendulum is T is 2 pi under root L over G. If you go to the moon, what changes? G. What happens to G on the moon? You guys have done gravitation. Tell me, is G on the moon more or less than G on the Earth? Less, right? The moon is significantly less massive than the Earth. So G is less. What happens to the time period? G decreases. T is 2 pi under root L over G, right? So it's inversely proportional to G. So if G goes down, T goes up. Thank you. Right. Fix the answer and let's move on. Okay, real oscillations. Ordinary day-to-day oscillations, right? We can consider any mass that's moving around to be an oscillating system. Like your hand, like this, right, is an oscillating system. Right? Looks like a pendulum, but it has some mass which is distributed, but it basically oscillates back and forth, right? The reason this is doing this is because when it's out of position, there is a restoring force, right? Gravity, trying to bring it back. Right? Overshoots, goes the other way. Does that make sense? Of course, once I start swinging my arms, it stops swinging. It's not like they're always swinging. Right? And that's what we call damping. Right? Most real oscillations are damped. Right? What that means is that they die out. Right? So you set up the oscillation and it dies out over time because there is a damping force present. Right? So far we have ignored friction, and as far as this course is concerned, mathematically we don't need to study damping oscillations. Okay? So I want you to understand this conceptually, not the math. Okay? For the math it's still just SHM and ignore friction. Right? But let's say we can't ignore friction in like a normal, ordinary day-to-day situation. Right? Then this oscillation will die out, right, over time. Everyone agree? Right? But then there's ways that this oscillations can die out. And that depends on how much damping is present. Right? So damping is a frictional force essentially, but it's proportional to the speed of the object. Okay? So as it's moving, there is friction acting on it, taking energy out of the system, which will eventually slow it down and it will come to rest at equilibrium. Right? So the motion of the system, yeah, I didn't do anything, it was its own thing. Damping looks like this, right? If I were to plot simple harmonic motion for a non-damped system, right, I just plot that sine wave forever, right? But for a damped system, if you look, right, this is what we call an under-damped system. So you set up the oscillation, you go to like an amplitude position. It comes back, it doesn't go all the way back to minus A, right? Because there's friction taking energy out of the system, right? So it oscillates a little and it slows back down, right? This is your standard example of like this, right? Start your arm swinging, let it drop, and, I mean, it doesn't come to a stop immediately, oscillates a little and dies out, right? So if I were to plot the displacement versus time curve of my arm, it would look like that. Right? And that's what a damped, well, an under-damped oscillation looks like. Right? A critically damped oscillation and an over-damped oscillation does not oscillate. Right? So theoretically, like those doors, right, in the back, they have springs pulling them shut. Right? So there's a restoring force when you displace the door from equilibrium. The spring is trying to close it. Right? Ideally, when we want these springs closing these doors, we do not want this happening. right? I do not want the closed door to do this, right? I want it to do this, right? Displace from equilibrium and come back to equilibrium without oscillating about equilibrium. Correct? Another case where it's really important to not oscillate about equilibrium is driving your car's suspension, right? As soon as you go over a bump, right, the suspension is there so that you don't damage your car. But after you've gone over a bump, if you're underdamped, you'll be doing this for a while. That makes sense? That's not fun, right? You want your car to go over the bump, right, displace slightly from equilibrium, and come back down to equilibrium as soon as possible, right, without an oscillation about it, right? That is what is critical damping, right? So a bungee jumping cord is like an underdamped oscillation. If you've seen videos of people bungee jumping, be careful Googling videos of people bungee jumping, by the way. Sometimes the cord breaks. Right. Anyways, so if you've seen people bungee jumping, right, they do this, right, and then they eventually slow down. Right? They're not doing that indefinitely. They're slowing down. So it's an underdamped oscillation. This is what an overdamped oscillation would look like. Right? You go right back to where you started slowly. Right? Critically damped is the same thing as overdamped, except it's faster. Right? A critically damped oscillation is the fastest way you can get back to equilibrium. Okay? Which is why cars are critically damped for suspension. So this is what that will look like, right? So it takes the least amount of time to fully damp out the oscillation. And examples are, of course, your shock absorbers. Like, there's a lot of oscillating systems in the world, right? I mean, your eardrums respond to sound waves because they oscillate, right? It's a drum, right? So what that means, it's a membrane that's oscillating back and forth, right? In response to sound waves hitting it. That's how you hear, right? So you hear that vibration, which is the sound waves hitting it, and then you don't hear it, right? So it is damped. It's not like they keep vibrating after they've heard the sound. Right? They're vibrating while the sound is hitting them. Right? After it damps out, so you don't keep hearing the sound. Imagine the same thing playing in your ears all the time. Okay, so tell me this. A certain system, mass on a spring, is oscillating in such a way that it's oscillating around equilibrium with an ever-decreasing amplitude. Is that oscillation critically damped, overdamped, or underdamped? So it is oscillating about equilibrium. Very good. If it's oscillating about equilibrium with a decreasing amplitude, it is an underdamped oscillation. Critically damped and overdamped oscillations do not oscillate about equilibrium. They go back to equilibrium. Right? There's so much friction that the energy is released in under a cycle. Okay. Click something. Right, now let's get to driving oscillations, and by here I don't mean driving a car. So what we've discussed so far, right, that T is 2 pi under root m over k. That's the time period of a mass attached to a spring, right? And we basically suggested that the same time period kind of equation can be applied to any oscillating system that's undergoing simple harmonic motion. Correct? Right. So what we've talked about so far is a natural frequency of oscillation, right? Which depends on k and it depends on m. Right? It depends on the oscillating mass and it depends on the restoring force. Right? So given a system and its environment, right, there is some natural frequency of oscillation. Everyone with me so far? Okay. Now, In a real system, there will also be damping. Right? So with that natural frequency of oscillation, there's also a damping term which damps out the oscillations. Right? So if I want to perpetuate the oscillation, I have to drive the oscillation. This making sense? And by driving the oscillation, I literally mean like doing this. Right? Instead of just doing this and letting it fall and damp out, right? You can do this. Right? You can literally make your arm swing. Correct? And you can keep that up till it falls off. Right? What you're doing is you're driving the oscillation, right? You are applying a force that is causing the oscillation to continue. Does this make sense? Right? So what we're doing is we're driving an oscillation, right? And when you drive an oscillation, what happens when you get close to driving at the natural frequency of that system is called resonance. Okay, what that means is, it's something as simple as this, right? If you raise your hand up, and I should probably be seeing you guys doing this as you're walking out the door at some point, raise your hand up and let it fall, right? There's a certain frequency to this oscillation. If you try and walk, right, and you try and swing your arm, when you swing your arm faster than the natural frequency or slower than the natural frequency, it takes more effort. Right? The least amount of effort will occur when you're swinging the arm at the same as the natural frequency. The natural frequency of this is letting it go, right? Like that. Right? There is a certain M, there is a certain K, so there is a certain frequency associated with my arm doing this. Right? When I'm walking, if I drive that system at that same frequency, it's easy to keep my arm swinging. Right? The same thing is on a swing. You've all been on swings, right? Correct? You don't need a person pushing you. You can pump your legs. Right? And if you pump your legs just right, you will increase the amplitude of the oscillation. Right? So you're pumping your legs at the frequency of that system. The system, of course, is you on a string. Correct? Like you are the bob in that case, oscillating back and forth. Right? But you pump your legs at that frequency and you get a large amplitude of oscillation. This making sense? We call that phenomena resonance. And resonance is important. It's, if you think about it, fundamentally molecules, right? Their masses attached to other masses by bonds which are essentially springs. Right? They're restoring forces associated with the bonds. Right? So with molecules as well, you can drive them at a natural frequency. Right? And for those of you who do any kind of spectroscopy, that frequency corresponds to an energy that's being absorbed. Okay? So even bonds have natural, like molecules, have natural resonant frequencies which they can oscillate. Right? And we call that phenomena resonance. So we drive by an oscillating force. If that oscillating force is also oscillating at the natural frequency of the system. So you're driving at the oscillating frequency of the system. Right? You're pumping your legs the right way. Don't worry about the math. You will never see that equation again. Okay? The only reason that equation is in there is if you look in the denominator, there's two omegas. Right? Omega 0 is the natural angular frequency. Omega is the frequency of the force that you're driving it with. Right? When those two numbers get close together, the denominator gets really, really small. Right? That's all we're saying. Correct? Right? If omega and omega 0 get really close together, omega minus omega 0 gets close to 0. Right? So the denominator gets really small, and if you look at the resulting amplitude of the oscillation, it peaks when omega is equal to omega 0. This making sense? So I can set up really large amplitudes in systems, right, in oscillating systems, if I drive them at their resonant frequency. Right? So I'm guessing a lot of you have heard about singers who can shriek loud and sing loud enough. It is a shriek, but to shatter crystal, right? And that actually is true. It does work. This is a slow motion video of that process. Right? So if you look, there's an oscillation. Right? Because this system is elastic. Right? It's driven by Young's modulus. You're stressing it. Right? So there is a strain on it, which is the deformation. Correct? But you're stressing it at the driving frequency. So if you can, there's a natural frequency associated with this, right? Related to its mass and its moduli, right? How rigid it is. Correct? If you drive it at that natural frequency, the resulting amplitudes of the oscillation that are set up can be enough to shatter it. This makes sense? Right? Because you're stretching it. Right? The amplitude is the displacement from equilibrium. Large amplitudes means a large displacement from equilibrium. Right? So if you can get a large enough displacement from equilibrium, you can break it. This making sense? Right? This is also telling you why bonds break at certain frequencies. Right? It's only when you hit certain bonds with light at certain frequencies that you can get them to break. Right? It's the same thing, just on a molecular scale. It's still a resonance phenomenon. Right? The fact that when the driving frequency is the same as the natural frequency, you can set up large oscillations. Everyone following that? Okay, so conceptually, you should understand critical damping, underdamping, overdamping, and resonance. Right? The fact that resonance happens at the natural frequency of the system. Okay, now let's go as promised and do questions that should be similar to the ones coming up on your exam. Okay, so over here we have the position versus time curve of a particle undergoing simple harmonic motion. Right? So on the y-axis is the x displacement, and on the x-axis is time. Right? So it's position versus time. Okay? For SHM, it should look like that. It can be sinusoidal. This is actually a cosine function, but that's also sinusoidal variation. Right? Okay. How do I find the amplitude of the oscillation? Amplitude is defined as maximum displacement from equilibrium. Equilibrium would be x equals 0. Right? So what is maximum displacement from x equals 0? 4 centimeters. Right? So the amplitude of this oscillation is just 4 centimeters. Everyone with me? Okay. Now let's see what is the period of the oscillation. What is the time period of this oscillation? It's the time taken for one complete cycle. Right? When you measure one complete cycle, you are free to do it any way you want in this graph, as long as it's the length of one complete cycle. Right? So if I start from here, right, one cycle is all the way to the other end, all the way back here. Right? So peak to peak. What is the time duration from one peak to the next? 4 seconds. Right? So the time period of this oscillation is 4 seconds. Right? You can do it from here. Right? If I start at equilibrium, one complete oscillation, like if I go from the 3-second point, starts at equilibrium, goes to one end, comes back to equilibrium, goes to the other end, comes back. Right? So one cycle is 7 minus 3, 4 seconds. Correct? Same thing trough to trough. It becomes 6 minus 2, 4 seconds. It doesn't matter which method you use as long as you cover one complete cycle. Everyone with me? Right? The easiest way is peak to peak or trough to trough. Okay? And then the duration is the time period. So if you know the time period is 4 seconds, what's the frequency? 1/4. Right? It's 1/4, which is 0.25 hertz. Everyone with me? Right? So reading a displacement versus time curve and plotting a displacement versus time curve for SHM is something that you should be familiar with. Okay? Now, let's keep going. This is a problem that I'm guessing a lot of you have already seen, right? It is a fish on a fisherman's scale. It is also what you guys are going to be doing in lab for the next couple of weeks, not with actual fish. You'll be hanging blocks from springs vertically, right? Fish stick. Okay, so my first setup here is to draw the diagram. Like after I read the question, I draw a diagram, right? And it's a vertical spring mass system, right? So this is my original spring, right? Unstretched. Okay, I'm ignoring the mass of the spring. Nothing's happening, right? It's my unstretched position of the spring, right? No forces, everything stable. Now I hang a fish from it, right? If I hang a fish from it, what is this going to do? It is going to stretch. Does everyone agree? When I hang a fish from a spring, the spring will stretch. So let's draw that. So after I've hung the fish, this looks something like this. And this is my fish. It's a block of mass M. Right? And we know the stretch in the spring. The question tells us that when I hang the fish from it, it stretches by 3.6 centimeters. Everyone with me? So this distance, which is the stretch in the spring, is 0.036 meters. Everyone's still following, right? Okay, now if I want to find the spring constant of the spring, which is a measure of how stiff that spring is, I can use the free body diagram of the fish at this location, right? Because at this location, the fish is at rest. Everyone with me? You hang a fish, comes to rest at equilibrium, right? This is equilibrium. So equilibrium, the two forces acting on the fish, the weight of the fish and the force of the spring, which is kx, right? X is the 3.6 centimeters that the spring was stretched by. And k is that unknown spring constant, which I'm looking to find, right? So at this location, I can say kx is equal to mg. I know m is 2.4. I know x is 0.036. G is 9.8. Substitute for k. And you should get that much, right? 653 newtons per meter. The point here is this is equilibrium, right? Because we've used the fact that mg must equal kx, the stretch in the spring, for this system to be at rest, right? And equilibrium is defined as the location where net force is 0, right? So this is equilibrium.
So x always applies to change from
No, x is the stretch in the spring, right? So at this position, the stretch in the spring is 0.036, right? So there is a spring force, correct? That's kx. It's what's balancing it, right? Such that the net force is 0. This makes sense? This is why for the horizontal spring mass system, the net force being 0, equilibrium was the unstretched position, right? Because for the horizontal system, gravity doesn't matter, right? In this case, gravity does matter, right? Because now it's a vertical spring mass system, right? And weight acts downwards. Okay, the next part of the question is telling you that from this location, I stretch it 2.1 centimeters and let it go, right? So the fish is hanging, and for some reason, I can't just let it be there. I choose to displace it by 0.021 meters. right? This location, and let go. What happens now? It moves up and down, right? Because I have displaced it from equilibrium, and when I displace it from equilibrium, there is a restoring force acting on it, right? It's further stretching the spring. Correct? So the spring is going to pull back up, right? And it's going to pull back up till equilibrium. When the net force goes to 0, the fish is going to overshoot it, go higher, right? So spring is going to push it down, right? This process is going to go on for a while. Everyone with me? Right? And that's what you're going to see in lab. You're going to basically be hanging masses from springs and measuring the amount of time these oscillations take. Everyone with me? Now, what is the amplitude of the oscillation? Is it 3.6 plus 2.1? No, it is just 2.1, right? Because the amplitude is defined as the maximum displacement from equilibrium, right? Equilibrium for this system is right here, right? The displacement from it is 0.021 meters, which means the amplitude is 0.021 meters, right? So it will oscillate back and forth about this position with that amplitude. Okay, so the amplitude of the SHM will be 0.021 meters. The period and frequency of the oscillation. Now, when you get problems for oscillations, there are only two systems you have studied: mass at spring and a simple pendulum. Right? So identify which formula you need to use. This is a mass on a spring. Right? It's not a simple pendulum. So we use T is 2 pi under root m over k. Substitute the respective values, and you will get that. Right? Once I have the time period, frequency is simple. Right? It's just 1 over that number. So F is 1 over T, which is 1 over that, which comes out to be 2.6 hertz. Okay. Oh, sorry. And plot SHM on an XT curve. So this is X, this is T. Should look like this. This is 0, this is 0.021 meters. And this is 1 cycle, so this is 0.38 seconds. That makes sense? Right? That is the plot of the motion. Okay. I have 2 minutes, and that is the time in which you guys will answer a question that was on last year's final. Clocks use oscillations to keep time, right? One of the basic functions of oscillating systems is to measure time. So let's say I have a clock based on a mass spring system, and I have a clock based on a simple pendulum, like a grandfather clock, which I'm going to cart to the top of a very high mountain, right? If I take both these clocks to the top of the mountain, which one of them or both of them are going to keep correct time? What changes between the bottom of the mountain and the top of the mountain? Sorry? Gravity is less, right? The further away you are from the center of the earth, the less gravity you actually feel. Correct? Which of these two timekeeping mechanisms depends on gravity? The pendulum. So the pendulum will not keep correct time. This makes sense? Right? It will be slightly different, probably not measurably so, but it will be different. Everyone agree? Okay. Good luck. I will see you guys on Monday. Remember, exams on Wednesday, and start studying. Exams on Wednesday, yes. You can take it.